So I've been thinking about logic a lot recently and the way that it just turns up in places all over the place and how we tend to use it a lot more than we think we do. Great examples when we cook. So let's say I want to make some spaghetti, and so I get a pot of boiling water and I've got my spaghetti, and I put my spaghetti in the water if the water boils, and then I've got this wonderful, delicious taste of spaghetti, and without logic I would never know when to put the spaghetti in or if I'd even get spaghetti. And we do that all the time. We're just like, okay, logic. And that's my favorite thing about logic, is I get to eat spaghetti, because spaghetti is delicious. But the problem is that sometimes logic doesn't always work, sometimes it breaks down, and I'd really have to say that that is definitely the worst part about logic. A great example of this is when you start trying to describe things with adjectives, because adjectives aren't really definite. They mean something to everybody else. So let's say you've got this city, and in this case it's going to be Pittsburgh, and you say Pittsburgh is big, but you're not really sure what Pittsburgh is, what big means. I mean, it's certainly big compared to this little sleepy town in the middle of nowhere, considerably East Texas, called Arkadelphia. That place is terrifying. But then on the other hand, you could have somewhere that's just huge, like it could be New York City with the Statue of Liberty, all these bridges and buildings, and it's huge. And so Pittsburgh, which seemed big before, suddenly just isn't big anymore. I mean, it's pretty big, but I mean, it's still big compared to Arkadelphia, but New York City is just so much bigger. And you just wonder, can Pittsburgh still really be big when it's not that big and compared to some things? Logic just can't tell you what to do, because logic says that either Pittsburgh being big has to be true or false. And is it big? Is Pittsburgh big? But maybe Arkadelphia isn't big either. But then maybe New York City isn't big either, because if you're just talking about the galaxy being big, then New York City isn't being big. So all these things seem to be true sometimes and false sometimes. You don't know when you can call it, and so sometimes you just kind of have to say, well, it's true or it's false, but then maybe it's not either. But thing is, logic doesn't have a way to say that it's not true and it's not false. It's somewhere in between. And so all these guys started saying, well, what can we do about that? Because we still have to be able to use logic even when we can't have these great definite things. And part of the terrible thing is that this isn't even always the only place where logic breaks down, because sometimes you ask a question genuinely just wanting to know the answer, but by asking you also assume all sorts of things, like there's a rainbow and there's people and the rainbow's gray, but who cares? And that's a bad drawing. But so let's say you've got you and your girlfriend, let's call her Sally, and you all were growing up for a long time, but your friend hasn't seen you in a while, so he thought that you were married, and so he asked us if you got divorced. But the thing is that you were never married in the first place, so you can't say that you got divorced. But if you say, did you get divorced, and you say no, then they think that you were married. Because there's no way in logic to say, well, actually, this happened. There's no precedent. There's no way saying, well, actually, it just doesn't work. And so some guy, a bunch of mathematicians got frustrated with this, and they decided that they just had to do something about this, because there was this huge gap in logic that just no one really knew what to do about. And so there was this guy named Lushkowitz, let's just call him Mr. L. He was Polish, so of course he had a crazy name. So Mr. L was thinking about Archimedes, and I mean, the big thing is that Archimedes was thinking about sea battles. And, well, not necessarily sea battles, but he was thinking about the future. And if you try and say there will be a sea battle tomorrow, logic says that either has to be true and false. So he's thinking about these ships that are going to shoot cannons at each other, and some of them are going to sink. But he wasn't quite sure if there was actually going to be a sea battle, but either there was going to be a sea battle or it wasn't going to be a sea battle. And if you say there will be a sea battle, you had to be true or false. But what if you couldn't tell? And if you could tell, then you could tell the future. And Archimedes didn't really like the fact that you could tell the future, because that just didn't really make sense. It couldn't make sense for you to tell the future when actually you just really couldn't tell the future. So clearly something bad was happening. So Mr. L was doing his thinking thing again. So he was doing his regular thinking thing. He was thinking, well, if it's not true and it's false, then it has to be something else. So he said, I'm going to call that I, because we just don't know what it is. It's going to be between true and false. There's true and false, and there's I. And I, it's going to be indeterminate, because we can't determine if it's true or false. We just don't really know, the future. We don't know what the future is. It's indeterminate. So he started drawing his truth tables. He was like, I got this I, now I gotta figure out how it's gonna fit into logic. And so he's drawing his truth table, he's got his A, and everything pretty much made sense until he started getting to the conditional, and so his truth table was a little bit different, but it worked out the best. And so there's a few that are just obvious because you just had to do regular and you got A and B and it was easy. And that all made sense, and you started trying to fill other things in, and it got a little bit trickier. And so since B was true, then it was no way for it to be false, and so it had to be true. And so then, but then the next one, if A was false, if the beginning one's false, it always has to be true, so that's definitely true. But then the rest we just couldn't really tell anything, so those were indeterminate. So we just still couldn't really determine anything when we didn't know anything, which made a lot of sense. If you don't know anything, you can't know anything. And so in the meanwhile, this other guy, this American, he was kind of inspired by Mr. L, and he decided that he was going to do something else. So this guy's name was Lotfizadeh, and he thought that Mr. L's system was pretty good, but you know, because even when things aren't true or false, some things are more true than others. And so he was looking at this problem, because the best things in math always come from problems, and he was looking at this paradox where it says, well, one grain of sand is definitely not a heap of sand, and I mean, if you just have one grain and you add another grain, then it's still not a heap of sand. So it starts to seem like if it's not a heap of sand, you add one more grain, then it's still not going to be a heap of sand. And then you just keep on adding grains and grains and grains, but it's still never a heap, but still somehow you manage with this pile of sand as big as your house. But apparently that's not a heap because there are no heaps by this thing. And that just really doesn't make sense because that seems to contradict induction. And even though induction isn't my favorite proof form, it's still pretty important. So a lot of people try to get away with it by saying that heap is vague and you can't really tell what a heap is. But if you've ever been to a beach, then you know, then if that's not a heap, then I don't think there is a heap. But that's so much sand. The beach has to be a heap of sand. And so, once again, so something had to be going on weird here, even though both the premises seemed to be mostly true. They had to be false eventually, but they couldn't always be false, because if it wasn't false, then everything would be a heap. It would keep on being like a heap. One grain of sand would be the only thing that wasn't a heap. And so he came up with this principle called fuzzy logic. So the reason why this is called fuzzy logic comes up later, but he was like, we're mathematicians, we should use numbers. I mean, I know we use letters for all these variables and things, but numbers have to show up somewhere, right? And so he decided, well, if you got something that's like, we say it's totally true, it's like a tautology. Like if you have a T, then it's T. If it's true, then it's true. If you're a T-Rex, then you're a T-Rex. There's a truth value 1. It's not true, let's get rid of true, it's just true. And so an example of this is like, say you're a horse, then you're definitely a horse. A horse is a horse no matter what. And then you've also got the totally opposite side where things are just wrong. It's like saying that if it's yes and it's no, it's false and it's not false. It's true and false. And that's totally wrong. So your truth value is 0. That'd be like saying that the moon is made out of cheese. The moon is definitely not made of cheese. If you try and say that, you're stupid, you're wrong. Truth value is 0. Disproved. And in 1930, there was this guy named Haytig, and he was thinking, well, I know what I'm talking about. I'm a highly trained mathematician, and I know that if I have a problem, then maybe I shouldn't just stop. I should stop just like bouncing around, looking in the face, and just get rid of the problem, because that's really what it's all about. And the problem is that we've got this true and false, but then there ends up all being all this stuff in the middle that we like to ignore, but really it's there. It's there, and it's got things like not T, and when we stop pretending that not T is just T is false. If it's not true, then it's false, but maybe it's not, maybe it's still kind of true, maybe it's like a little bit, and so not T is, I don't know what it is anymore, and so even if it's not, it's still just not, it doesn't end up being just not in, it's not anything, it's nothing. Except, yes, it is. It's just there in the middle. It just, everything ends up there in the middle, and you can't simplify down like we like to with that ain't got none rule. Which kind of makes sense, because say you're a horse, and say you've got this horse, but it's not a horse, then I suppose it could be a zebra? But, which, I mean, it is a horse, but it's not what you were talking about originally, because really what you're talking about when you said not a horse is you just wanted a horse. But you got the zebra, and that was still right. The same thing happens with me in honey locust trees, so I would say that I'm not the honey locust friend, but every time I try and give it a hug, the same thing always happens. I have to end up going to the hospital. And I have to say friends don't make friends go to the hospital. So back to fuzzy logic, because it's clearly the best. Because it's like real life, because instead of you've got like something that are more true than others, and you have this whole scale from true to false, and it's all in the middle. You have all the way from like liar, liar, pants on fire, wrong, to honest Abe, honest, true. And it's just like real life also in the way that when you start adding together things that are like kind of true but mostly true, you end up getting something that's like even less true than anything that you started with. It's like multiplying fractions. It's like math because there's numbers. And so important thing the numbers is that Zade made this whole table of things that for figuring out the truth values of things using other things. And so back to that sand paradox I was talking about earlier, if I can just find it. Oh, here it is. Okay. So remember, you've got this heap of sand that somehow ended up bigger than a house. This pile of sand that somehow ended up bigger than a house, but still wasn't a heap. And so how did that even happen? How exactly did you end up with a pile of sand that was bigger than yourself? So you've got this one grain of, because that's definitely a heap, and so imagine you've got this one grain of sand, that's definitely not a heap, so that's definitely going to be a truth value of 1. But then the other side, when you've got another, not got a heap, and you add a grain, it's still not a heap, that's like almost usually true, it's almost always true, but it's not quite, so let's just call it a 0.99 value. But the idea that there's no heaps, that is so wrong. That's a heap. Right there, truth value 0. So in the conditional A implies B, if B is less true than A, which is how it is in the sand paradox, then the truth value of the conditional is going to end up being the differences of the difference of the truth values of A and B, subtracted from 1. Because it's going to be less true than totally true, because it's going to be true sometimes and then not true other times. And so with your first thing, if your A, if true, then not heap, and then if it's not a heap, then it's still not a heap, you keep on applying this rule. And so you started just being 1 minus 0.99, which is 1 minus 0.99. You keep on repeating this rule and just totally goes to 0, which makes sense because you just keep on getting sand and you do have heaps. And so that resolves the paradox. And so, but you remember that part where you just kind of said, yeah, that's going to be 0.99. That kind of, the thing is that kind of happens with everything in this system. Like you just kind of like choose some numbers, and once you got those numbers, then you definitely know what to do. But before that, you just don't know. But this isn't the only system that just doesn't make sense. Because in the K3, which is the first time, you just do your truth values, and most of the table makes sense. But that indefinite in the middle, that's like saying that if the king of the USA is bald, then you can't also say that then the king of the USA is bald. Like that's still indeterminate. And then for the other one, you've got not red, but I don't know if anything that's not red besides red, is that not red? No, that's definitely not normal red. So we can say that like many valued truth systems, there's one problem. It just ends up they just have too many truths. It's like introducing too many variables into an equation, and suddenly you can't solve it anymore because there's just no way. It's like trying to solve a system of equations that has more variables than actual equations. You can never come up with a real answer. So as much as these guys try to make a functioning logical system, they just don't really work. That's what I'll say to my truth functional logic for now.